Okay, start my talk. So today morning I will introduce how to using some domain decomposition method to solving some Maxwell eigenvalue problems. So it's already known the Maxwell equation is very important for the engineering and the computational mathematics. So how to solve the eigenvalue with the Maxwell operator? This is very important, also very difficult programs. Actually, this is a joint work with my students, and another is Professor Shangyu Zhang from the Delaware of the USA. So this is the outline of my talk. I will introduce three parts of this in this talk. In the first part, I will introduce what is the overlapping Schwarz method, or what is the domain decomposition method in H1 space. And then in the second part, I will move to how to construct overlapping Schwarz methods. This is a special domain decomposition method in H-curve space. And finally, I will using this above method to solve this Maxwell eigenvalue problems. This is the last part of my talk. Okay, in the first part, I will introduce the overlapping Schwarz method in the H1 space. H1 space is a subspace space. Okay. First of all, I introduce this domain decomposition method. It's well known the domain decomposition is a very powerful method. This is a parallel, a potentially fast and robust algorithm for solving the linear or nonlinear equations that may be arising from the approximation of the partial differential equations by the finite element method or the finite volume method or something spectral method, something other like. So actually, this method is first proposed the very famous mathematician Schwarz in 1860s, and then in the 1988, very famous mathematician P.L. Lyons feels medal as this, and they propose how to using this method to solve some partial differential equation. Actually, he named this method on the Schwarz alternating method. I will introduce later what is the Schwarz alternating method. And in the 1980s, this is a very famous conference, the domain decomposition method conference. Actually, every 2 years, this conference will be organized in different countries. So in the third conference, Professor Lyons also proposed a non-overlapping Schwarz alternating method. They first proposed overlapping Schwarz alternating method, and then finally he proposed no-overlapping Schwarz alternating method. Of course, there are lots of books and some review papers on these directions. So I just list two very famous books written by the F. Smith and the Bajorsta groups in 1996, and another one is Toselli Wendland in 1999. This is a very famous book. Every student, if you would like to learn some domain decomposition method, there can be learn something from these two books. Of course, there are lots of some review papers in these directions. So there are lots of advantages for these methods. Actually, this method is a potential for efficient parallelizations for this method. And this method also have some ability to deal with partial different equation on very complicated physical geometry. You can use this method to deal with some very complicated physical geometry, and then using the domain decomposition method, decouple this complicated physical geometry by some simple physics geometry can deal with this partial different equation using this domain decomposition method. Of course, this method is very important advantages. We can use this method to design some superior convenience property of the iteration method. That's meaning we can use this method design some preconditional to speed up this standard iterative method. actually this is also. And for example, if your multi-physics programs, for example, you would like to solve some plot and composed physics, like this desk, you have this one, this is plate, and another one is this node. So you can decouple by the domain decomposition. In this case, the interface is very important. In this case, you should deal with this simple geometry. This is the domain decomposition method. This is very good, reasonable ideas. So if you solve this model problem, for example, we give the very simple model, the linear and elliptical partial differential equation. So the LU equal to FL. That means the L means the operators, elliptical operators. Boundary condition is BU equal to G, and this is partial differential equations. Or we can using finite difference, finite elements on the spectral method of the volume to approximation these partial differential equations. First of all, you should give the variational form using this Green formulation and other formulation. You can get this variational form. For example, you can U belong to the V is some superfluous space. Maybe if the second order equations, the V is the H1 space, and this is get this variational form. This is some simple example. For example, if you just consider the Poisson equations, of course, you say V is exactly the H01 space, and in this case, the variational form like this, and in here, the bilinear form can be written down like this. Okay, write down like this. This is very simple. Every student or the master degree student can be done like this. Now we will introduce this Schwarz alternating method. This is we just first of all we just show you the two subdomain case. In this special case, if you would like to solve equation on the whole domain like this, whole domains, so we would like to using domain decomposition methods solve this equation in this formulation. So we first of all partition this whole domain into two subdomains. This subdomain may be more regular. So in this special case, the first subdomain is a circle. So another subdomain is rectangle, right? In this case, this is the overlapping size. This part is overlapping case. So in this case, you first solve this equation in a circle, okay? And they give some initial values. For example, U2, 0. You can obtain this solution in these circles. You can get the U11, okay? And then you get the information in this region, in this subdomains, and the restriction in this boundary, because of the whole domain outside equal to 0 boundary condition. So this U21 is exactly equal to U11. So you solve this equation in this subdomain, okay? And then this get the information in this boundary gamma 1, and you can continue to solve this in the circle, and then get the information gamma 2, and you can get this, solve this equation in this rectangle. This is Schwarz alternating and solve these two subdomains. So you get a series UN. So this UN you should prove this is convergent to original equation solution. Right? So in this case, this is a very important idea from the Pierre Lyons. He introduced the projection. This energy projection from superfluous space H01 to the subspace H01 omega I. This H01 by the zero extension is exactly subspace H01. So you can define this projection, this PI. This is energy projection because dependent on the bilinear form AI. So actually the above Schwarz alternating procedures can be expressed as the error estimator using this projection right down like this. Okay, this is very famous. And already Pierre Lyons proved this convergence right. You just estimate the norm of the operator. Already proved this convergence is very fast. Actually, this is 1 minus 1 over C0. This C0 is exactly depend on the overlapping size. This is size. If overlapping size is large, the convergence is more fast. This is reasonable. Okay. Actually, this is the result of the Pierre Lyons. But for the computational mathematicians, we don't focus on this point. We should using the finite element and the finite difference to approximation original problems. So this is for the computational mathematicians. We can consider how to using the idea to design a very fast algorithm to solve the original equations, partial different equations. So in this case, we should be considered many subdomains. Why? Because this is very important of parallel computing. We can using my process on the subdomains solve this local problem together and combine together. This is the idea of using the domain decomposition method. So actually, we should be considered many subdomains. The two subdomain cases just the ideas. So in this case, we can let the omega L equal to 1 to capital N be the cos shape regular, cos uniform partition of the omega when we denote it by the T capital H. For example, if we solve a partial differential equation on these whole domains like this, we just for simplicity, we just consider this rectangle like this. We first of all, we can partition the whole domain, get a cos shape regular cos of the partition for omega. We call this omega L. In here, this is just a 9 partition omega L. This is dashed line like this. Okay. This is only 1, 2, 3, 4, 9. This is omega L. This is subdomains. You just first of all do like the cos space or cos partition of the omega. We may define this HR as the diameter of the omega L. And thus, this is the cos partitions. We would like to solve this equation. In this case, we should continue refinement. This cos measure. This is the fine partitions. Okay, that's meaning with the fine shape regular and cos uniform partition T small h is obtained by the subdividing this T capital H. Okay, so in this figure, show you this is small one. This one is a partition, a small partition. We using the bilinear conforming finite element to approximation the original partial different equations. So obviously, we know they constructed the finite element space. V capital H should be belong to the V small h on the T on these partitions. And then another problem is because we consider the overlapping Schwarz method, so we should be construct an overlapping domain decomposition. So how to get the overlapping subdomain? We denote maybe omega L prime. We can just very simple enlarge the subdomain omega L by the adding the fine elements layer by layer. Such, for example, in here you can just enlarge one layer. This is gray. This subdomain is the all subdomains. So we denote this distance denotes this enlarged size to measure the overlapping size between the neighboring subdomains. Okay. So we also assume that capital HR is the diameter of the omega L prime. So this is gray subdomains. Okay. This is we would like to solve this subproblem in these regions or this is subdomains. Okay. Actually, we in this spatial case, very simple case, we have 9 subdomains, omega L prime. Okay. In this case, just for the Poisson equation or the Laplace equation operators, we can get the local subspace. It is very simple. Just this whole domain. If the VH, this is VH, we just restriction this omega L prime on the H01. This is directly explanation because this is 0. omega L prime. The omega L prime, this is just enlarged these subdomains. We can define this as subspace because we should solve this. This core domain case, we cannot solve it. Now we can just solve this small one. Okay, now on this small space. So first of all, we gave some operators. We can define the AH is on the whole domains. We would like to solve this AH inverse, right? This is we would like to solve it, but we cannot because it's very, very large matrix. So in this case, we can just define this small one, this A small, the capital cos space, a capital H. AL is on the subdomains. Okay, now, so we can define this one level Schwarz method. For example, the identity Schwarz preconditional. In this case, we just only solve this AL minus 1 because AL is a small operator on the subdomains. So we can solve it by some parallel computing very easily. But we cannot solve the AH minus 1. This is very large. So now we get a preconditional BH1 minus 1. So we can multiply this AH, can get this PUL is a projection. This is introduced by the Pierre Lyons. This is a very famous additive Schwarz preconditional. And this is preconditional systems. The problem is, if you would like to go to preconditional, you should show everyone that BH minus 1 is very easy to computing. So another important ingredients, it should be the condition number. BH minus 1 AH is smaller than the original condition number AH. This is a very key point. Of course, we can also design some multiplicative Schwarz precondition. This is some that I just showed you in the two subdomain case. This is Schwarz alternating method because you can see the I minus BA exactly 1 minus I minus P1. So in the two subdomain cases, this is N, capital N just equal to 2. Okay, I just show you. This is the many subdomain case. So if you would like to estimate the condition number, I just said, if you would like to estimate condition number, you should be make some assumptions. As that means the partitions, the omega prime, this I just show you agree these subdomains may be colored using at most N0 color in such a way that the subdomains with the sum color are disjoint. So actually the integral, the N0 is independent of the whole number of these subdomains. For example, the number is 1,000 one subdomains, but the N0 just 3 or 4 color can be covered. We can prove the condition number exactly is C1 plus 1 over delta square. So the delta is the overlapping size. I just show you overlapping size. The convergence rate is like this for the multiplicative case. Okay. So because this is one level case, but for the computational mathematicians would like to optimize these procedures, we should be introduce some global program on the cost measure. So this is the famous two-level Schwarz math. Many computational mathematics work on these directions. This precondition is just very simple, just add one term. This term just you solve a cost programs because we already partition the original program of cost space. So we can solve this cost space and plus the one level additive Schwarz. This is sum of the above one. You just add these terms. We call this this method is two-level Schwarz method. And then the condition number can be improved like this: 1 plus capital H square over delta square. And this is what kind of equations?
Oh, so you need this precondition for the method to work, right? So I assume that there's large classes of differential equations that satisfy this.
Yes, should be satisfied this. Okay.
Yeah.
Okay.
Not all systems of equations.
Oh, not all systems equations. Just in here, I just show you these second order equations. Not for just for the maybe should be definitive.
Is there a particular area where this
Not all equation can be satisfied. Only in here we just show you the Poisson equation on for second order.
That's an example.
That's example, not for all. For the non-symmetry equations, but cannot not like this. But we can also similar. But this is different in this. You cannot, for example, if you design precondition just using CG method to solve these equations, you should be estimated these condition numbers. But the non-symmetry or indefinite equations maybe cannot do like this. But for example, if you solve this more complicated equations for this, how to solve the equation, this is still lots of programs cannot do in this method. Of course. Yes. Just for they can be done like this. Yes. So just to show you, this is we say this 1 plus capital H square over delta square. You can this is square in here. We don't like it. Why is it? If you consider you can remember we just for the subdomains we just extend the one layer for obtain the subdomains omega L prime. So if you just the one layer, so this delta equal to small h. So here is h small h square over the capital H square. So this is not a good result because for the original one, it's just 1 over h square. So you improve not too much if you just look at these formulations. So actually, in the practical computation, using domain decomposition method is very fast. So the computation mathematics don't understand why. So actually, the July and Windland in 1999 already for the special small overlapping case, that's just a small layer extension, one layer. So already prove the combination can improve 1 plus capital H over delta, no square. Okay, no square. This is a very good result. That is increase the linear, not this quadratic. This is a very important result. And Susan Brown, she also attended this conference. I think maybe go back now. He proves these above estimates are sharp. You cannot improve. This is the best result. Okay, you cannot improve. This is very interesting. Of course, this is very technical. You should be improved it. Now of course, just the question is we may apply application to the other model program. For example, the high order program, the plate bounding program. This is also brand prove this result is already design some algorithm, including Maxwell equation, non-symmetry indefinite program, nonlinear programs, nonlinear biharmonic equation program, including Navier-Stokes equations, also including some eigenvalue programs. We also work on this direction many years, design some domain decomposition to solve this elliptical eigenvalue programs, including today's talkers. We will introduce how to introduce a Maxwell eigenvalue program to solve this, using this method to solve the Maxwell eigenvalue programs. There's lots of applications in these directions. So now we will move to the second part of my talk. This is just consider this second order program. Now we will move how to using this to solve these Maxwell equations. This is more complicated from the computational point of view, because you should be how to approximation this H-curve space. H-curve space is much more difficult compared to the H1 space. So the problem is sum. With the same situation happens to the analysis of this two-level overlap Schwarz in H-curve. Actually, the Toseli and Windland prove the upper bound is equal to 1 plus h square over delta square for the condition number. But for many years, maybe the 20 or 30 years, people wonder whether the base bound should be 1 plus h capital H over delta. This is whether this situation also same as the two second order programs for especially for small overlapping case. already numerical result indicates that the best bound should be like this, but nobody know how to prove this way, this one. So actually, for the computational mathematicians, or if we cannot prove it, we can do some numerical result to show this whether this result is right. This is a picture. This picture not did by myself. This is actually a picture from the famous book from the Toselli and Wendland. This is a very famous book from domain decomposition method, algorithm, and theory. I just show you at the beginning of my talk. This is a very famous. Every student, graduate student, if you would like to learn some domain decomposition method, always read this book. And this is a picture from this book. Here's just to show you this two-level method for the H curve Maxwell equations. The inverse of the minimum eigenvalue, or you can say the condition number of the preconditioned system. If we do, you can look at this direction. This is H over delta. I just show you H delta. If we go to 0, this denotes this large overlapping. If they go to this direction, this is small overlapping. This small overlapping. You can see this is by this least square fitting the polynomial. For this large overlapping, this should be constant because the H over delta is also equal to O capital H. This is constant. But for this small overlapping, this is in the over this is a small h. In this case, should be should be equal to 1 plus capital H over small h. This is you can see the solid line is this is linear. This dashed line should be the quadratic. This is dashed line. Actually, this is if this point is by the numerical result, this show you should be a solid line. Okay, by this fitting polynomial. What this meaning the numerical result indicates the base result should be 1 plus capital H over delta. This is from numerical result it show you, but you cannot prove. Everyone estimate just like this, and this is the programs. So not the error. Not the error. This is show you, just to show you. This, for example, this is point is computed by the computer. So we're using the least square method. Least square method. You can see the least square method. This should be the inverse. Such the condition number is the sum. This is the inverse of the minimum eigenvalue. Should be this direction H over delta. This is for this. If this become large, this is a small overlapping case. If we go to these directions, go to 0. This is a large overlapping. That means that delta is go to capital H, went to these directions. So already you know if the delta is H, capital H should be constant. So you can say this is constant, 1 plus. But for the small one, the delta become small. Should be linear, not the quadratic. Dotted line, this is quadratic, but this show you this is not quadratic. This is not quadratic. This is linear. Not 1 plus. Not 1 plus 1. Just to show you H delta.
Okay, I understand. Maybe that.
Yeah. Just to show you this linear increase both this H plus delta.
They're all below 1 and 1.
Yes. Okay. This is to show you. Just to show you, very simple. By the computation mathematician to make some numerical result to show you this exactly is linear increase. But we cannot prove it. That for the computation mathematician always like do some numerical result to show it. So many famous computation mathematicians also found this problem. Graham posed this is the open problem. If the base whether this base bound should be C 1 plus capital H over delta. He said, note that in the Helmholtz equation, Helmholtz is second order equations. So the factor capital H delta square can be replaced by the capital H over delta. This I show you is Susan Branner and Wendeland also proved this. But this feature has so far not been established for the Maxwell case. This sentence is just from his articles. For these reasons, it depends on GM-race bounds on these terms is worse than that in the Helmholtz equation. This paper is published in the Mass Computational in 2019. He said this is an open problem, cannot prove it. But actually, we said this can be proved. I just show you. If we consider this one is the Maxwell equation, this is very classical Maxwell equations. You can find U belong to H0 curve such that this is formulation like this. This is a standard Maxwell equation, very famous. Okay, the H0 curve is meaning this boundary condition like this. Okay, so if you for the computational mathematicians always using some formulation approximation the form. So in this case, we always choose the Needlerich element approximation these Maxwell equations. This is a normal way. Sometimes we can call this edge element. This is if you do some Maxwell equations, this is very famous. We consider the case Needlerich elements for approximation the H0 curve. Okay, and then we can get a approximation variation form like this. If this Needlerich element space UH satisfies these formulations. Similar as this second order program, you can define this AH. AH also is a Hall operator. We would like to how to solve this AH. This is the main purpose. But we cannot solve this AH, so now we should choose the domain decomposition method. This is the main idea. Okay. So in this case, we now introduce this two-level Schwarz method for solving these Maxwell equations. Because the first part is we solve the second order equation. Now we solve the Maxwell equation. We're using the Needlerich elements to approximation the just equations. Similar as this, the second part, the H1 space, we do some restriction. In this case, we restriction on the subdomain, the omega L prime. But in this case, we should be considered in the H curve space, okay, not the H1 space. Similar as the H1 space, we can define the cost space AH, but every approximation should be in the Needlerich space because your approximation summation H curve space, okay. AH, similarly, we can define the local space, local operator, the AL on the subspace. VL is defined like this on the subdomains, this gray subdomains. So the preconditions similar as the second order equations can be write down like this, the BH1 minus 2. So actually you can solve, you can see this, in this case we also just solve this cost space and subdomains operate programs. This is we can parallelize using some computing to solve this problem. You cannot solve a global program, you just solve a subdomains program. This is the idea. This is also parallel computing. So actually this is preconditioned. The problem is that we should prove the condition number also very good, right? This is the main point. So we should be proved this is, I just show you 1 plus capital H over delta. Okay, so we should introduce a very important lemma. Actually, because this omega W not belong to the global H1, just belong to H curve, because H curve space is larger than H1, right? So in this case, but we can prove a lemma just on piecewise H1 space, H1 function. That means on the global domains we cannot prove, but we can on the subdomains. On the partition of this cost space, this is a piecewise H1 functions. So you should be prove this result. Actually, we prove it because we prove this result, so everything is okay. So if W belong to local H1 omega L, For example, this if we partition triangle, this is omega L, like this. So your extension layer, this is omega L prime. Because in the first part, we consider this rectangle, now we consider triangle. This idea is similar, okay? So this omega L delta is the omega L delta is a layer of the small elements should be the boundary of the omega 0 prime, okay? This is omega L delta is just the neighboring around this boundary of the subdomain, around the coarse element, okay? This is this one omega L delta. We can prove for one of omega L0 delta, this is controlled by the, have an up bound like this. Can prove like this, controlled by the H1 norm and L0 norms like this. So see, this is the sum J equal to 0 to I0. The I0 is the sum is omega L1 omega L I0, and the I0 is the neighbor subdomains which has no ambit intersection, like this. I show you, like for all these situations, for this one is omega L0, like this. So extension usually intersection not 0. This means all of the omega L0. In this special case, we have I0 is 12. Extension should be interaction should be not the ambit in this case, very special case. So this is show you this I0 in some simple situation should be prove this lemmas. After you prove this lemma, this result, you can get this main result. If later final overlapping assumption hold, and the color should be satisfied. Then for any VH, if it belong to nether elements, you can prove this result. You can hear this in here is capital H over delta, not the square, just not no square. So we can prove this precondition condition number is exactly is C is 1 plus capital H over delta, not the H square over delta square. Okay. Oh, see, so this is the result already published in the IMA General Numerical Analysis, the British journal from the Oxford, right? This year, just the year, you can see just published. Of course, the archive already proved. This is actually you already proved this open program for this many years, maybe 60 years. Many computational mathematicians would like don't know the result. Now finally we can prove this one. This actually the key ideas in analysis. The key idea is obtain the shape estimate of the overlapping on the H curve. So the functions are limited to one element of the coarse triangulations, where all functions are H1 locally. This is the key point. You should be proved not global the H1, just the locally H1. Piecewise H1, you should prove the lamp. This is when they can get a shape estimate, then they result in iterative. Very simple, but nobody realizes this point. This is very strange. We can, by the Helmholtz decomposition, we can get some subspace in H curve, which is also H1 when the omega is convex. So now we just prove the global omega should be convex, not convex should be some other technical. We believe all right, also right, but convex is now proved these papers. Okay, last one we move to this Maxwell eigensolvers. We just using the second part result to show you. So actually, it is still a very challenging program to solve the large scale eigenvalue problem. In addition, dealing with the kernel of the curve operator for the Maxwell eigenvalue problem. So the problem is we should be computing the multiple and cluster eigenvalue of the Maxwell eigenvalue program that has encountered lots of troubles. So from the polar point of view, the domain decomposition method is a good choice for solving the large-scale eigenvalue problem. This is a very difficult problem, but anyway, we can how to solve this problem. This is still because we not only hope to obtain one eigenvalue. We should solve multiple eigenvalue, but this multiple eigen may be the classed eigenvalue. This is quite difficult to obtain this eigenvalue. So this is a very classical Maxwell eigenvalue. In this case, the governing the equations can be look like this. This is typically the eigenvalue program. This is curl operators. This lambda is eigenvalues. You should be solved this. So eigenvalue program for the computational mathematics is very difficult, because this is nonlinear programs. So in this case, n denotes the outside the unit norm vector along this boundary. Okay, epsilon r is relative to this electrical permittivities. Okay, the mu are the relative to the magnetic permeabilities. For this spatial case, maybe just consider epsilon and mu just equal to 1 for simplicities, if you consider it. So Maxwell eigenvalue problem, you can write the variational form, because we would like to using the finite element method to approximation these equations. So you can use this one as write down like this, and this binomial form can be written like this. The alpha is larger than 0. Okay, this is a variational form. So the eigenvalue and the eigenvector, we can first define the operator T0. T0 will satisfy V like this one from this H0 curve. I just show you this space intersect H diff 0. If we define these operators, we can show you that T0 is safe adjoint and compact. The compact is very important. So by the help of the Schwarz theory, we know the eigenvalue can be written down like this. Of course, the first one is larger than 0. And then the corresponding eigenvector can be denoted like this. This is the eigenvector. Of course, according to the binomial form, it should be orthogonal. We denote the right gap for the lambda I by the lambda I plus equal to lambda I minus 1 minus plus 1 and minus lambda I, denotes the gap of the lambda I. Because the convergence right depend on this gap. Okay. So the discrete variation form, similar as the Maxwell equation source programs, we can also using the Needling element approximation this variational form using for this eigenvalue problem. You can prove this. You can write down this formulation like this, and the Needling plus denotes this is orthogonal complement space for this finite element space P1 conforming finite. And this is the classical one, and actually you can write a equivalent form like this. Okay. You can also for the discrete levels, similar as continuous levels, you can write down this formulation like this one. Okay, this is the eigenvectors. Finally, we can quite technical. I don't show too much in here. Okay, this spectral decomposition, this spectral projectors like this, and then there are lots of eigensolvers. I don't show you too much on here. For the second order problem, two-grid method, multi-level method, multi-grid method for the eigensolvers. So now these two-level parallel Helmholtz subspace iteration algorithm. You first solve cost programs, cost eigen programs, and then you can solve this small eigenvalue programs on these programs, and you can do some tolerance and then return to iteration. So the key point in here is you should be designing the preconditional like this. This is some of this source programs. Okay, source program. So this is obviously the assumption, two assumptions for this eigenvalue programs. You can prove this is my students can prove this eigenvalue is convergence, eigenvector also convergence very fast. Okay, so in here this is dependent on this parameter. This parameter depends on this 1 plus h of delta z squared. Now this square can be cancelled. You don't need it because of the second part. This paper already published in some numerical analysis 2023. Okay, if you would like interesting, you can look at. That also difficult in the analysis. I didn't give the too detail in here. So I show you some numerical results. This is very stable. Okay, if you just the 2D case, you can see the optimality. Actually, the degree of the matrix from the ones over the 12,000 to 12 millions, very large matrix. Okay, if you don't use the domain decomposition, you cannot solve it. So you can see actually this is already 6 curves and fixed together. That's meaning this method is very stable, very stable. As which meaning is very stable. This is the scalability. Okay, that's meaning if you're using the computer over the 100 to 2,000 computers, the result you can see very fast convergence. We can also extension the 3D case. You can see if you solve this 11 eigenvalue together from the 33,000 to the 18 millions degree of freedom, very large. You always need 34 iteration steps, very fixed, just the same. Don't depend on the size of the matrix. And this one is the eigenvalue. You can solve very accuracy. Okay. This is scalability also show you the 3D case. The effect of the shift alpha also is very not very incentive. Okay, incentive. Always 35 from this one to 1 because but the alpha not to choose too large. If you choose too large, the iteration number become very large. Cannot choose. But the alpha you can choose by yourself. Normally we can choose 1 is okay. Very fast, very fast. This is my talk. Very fast. Okay. Because I think nobody understand it. Thank you, the chair in my talk.
So, do we have any questions either in the room? I think questions. So I can ask a very naive question.
No,
so,
not.
Earlier in the week, I attended a talk on solving high-dimensional differential equations using deep learning.
Yes. Lots of people now.
The idea I got was that they're essentially estimating around certain points. They just want solutions in very controlled certain regions. And yesterday, I attended a talk where they were thinking about, I guess it was dimensionality reduction using sort of ideas from differential geometry. Sort of seeing the domain as a manifold and having training several networks that have transition functions. Similar ideas. So I guess the naive question was, would they, you were solving very specific differential equations by explicitly splitting up the domain and getting exact solutions.
Yeah.
So I was wondering, is there possibly a way that these sort of ideas could be weakened to get approximate solutions to differential equations that maybe don't have as nice preconditions?
Sure. It's for this more complicated geometrical physics, like you show me, there's a very maybe different manifold. If we may use, first of all, you should be using for the computational mathematicians. We should first using some finite element method. Finite volume should be approximation this complicated geometry. And for example, if using the manifold, this is very difficult to using the finite element. The geometry is difficult. So sometimes you choose, many people use deep learning. This is why we use measureless approximation. In this case, you also can using the domain decomposition to approximate this very complicated geometry. We already did some result. I don't want to show in here. We're also using, for example, using on the subdomains, using some machine learning method to solve this in these subdomains. In another way, you can using machine learning to solve this geometry manifold. The formulation is quite complicated. Using the finite element, you cannot do it because the geometry is already default. So in this case, but you can using machine learning. But
you also learn the subdomains as well.
Yeah, as well. So, but you should be very careful with the interface. because the interface should be exchanging informations, different subdomain. You can imagine. If you cannot imagine, you cannot convert to original the solution.
It's like transition.
Yes. This is very fast in the interface. Yes, this is very technical. In this case, how to exchange the information in the interface? In this case, you should choose a different formulation of this variation of form. You know that deep learning solves the partial normally have two methods. One is pins. You know this one method. Another one is deep lease. These two methods. So you should be choose deep lease formulation. You can exchange the information on this interface, and then you can solve this. We have just published a paper in some scientific computing, maybe 1 month ago. Just that is show you. This is another interesting talk. But how to solve this equation? This is very technical. You should be using one domain is machine learning, another one also choose machine learning, and the interface based on deep lease method. Exchange the interface. You can solve this. All right, no problem.
Thank you very much. Thank you again.
Thank you.